Hello? Okay, thank you. So since its inception, gradual typing has promised programmers that they can get the best of both dynamic typing and static typing. So if we start with some untyped program, like the one represented by this module dependence graph here, then ideally we can just slowly add types to different modules and take advantage of static typing along the way. But unfortunately, this doesn't come for free. Along the way, we have to deal with interactions between typed and untyped components. So for example, let's consider a typed add function. So we have a curried add function that's just going to add two floats together. And we want to use this in an untyped program. Except the untyped program has forgotten that add is supposed to take floats, so they try and add two strings together. If these are both dynamically typed programs, then when we run them, we would probably just get some dynamic error from plus saying that you can't add two strings together. But we'd like to be able to take advantage of the fact that we've written add in a type language. So we'd like to be able to do some type-driven optimizations. So maybe replace plus with an unsafe version that's specialized to floating point numbers. But if we do this and then run our program, who knows what's going to happen now, because it's going to depend. We just don't know. So we need to guarantee that add is only going to be called with floats. And one way to do this is to protect our function with a contract or a cast or some form of runtime proxy that's going to ensure that only floating point numbers can be passed to add. So in type bracket, we'll stick a contract here that says, I expect a float, and I'll give you back a function from float to float. So now if we run this program, before the function's even called, we'll get an error message that says, I expected a float, but you gave me a string. And this is the fault of the untyped program. So this works, and this gives us sound gradual typing, but this comes at a cost. We've added these checks, these new runtime checks to our program, and this can have severe performance penalties. At POPL in 2016, some colleagues published this paper, which does a large-scale performance evaluation of gradual typing in the context of type bracket. And they found that along the way of typing some programs, you can get overheads as high as 120 times as slow as your original untyped program. So there's definitely something wrong here and something that we would like to be able to fix. So let's take a little bit deeper look at what the problem is. So now let's suppose we have an untyped add function and we want to pass it to some typed module, again with the same type, float to float to float. When it goes from the untyped module into the typed code, the type has to be converted to a contract that's going to protect uses of add. So it'll be converted into this contract that will just check the float predicate at every time it's called. But what happens if this passes back into untyped code again? It's going to get a second contract. And if it goes back, we're going to get a third contract. And this will just keep happening over and over again. And we're going to be building up contracts that check essentially the same things without any real benefit. In this specific case, it turns out that these contracts on the right are actually exactly the same. So there's no reason that we should need to actually keep building up contracts over and over. But we can't just drop them in general, because what if we have more modules? So here we have two untyped modules and a typed module in between. The same case as before, we'll put a contract on it when it flows into the typed context. And now if it flows into a different untyped module, we'll put a different contract. We'll put the same contract, but it's crossing through a different boundary, so I'm going to use a different color here. And this one, we can't, this isn't, we're checking the same things, but we can't replace either of them without changing the behavior of the contract. So why is that? Let's talk about contracts in Blane for a second. We can think about contracts as dividing the world up into two pieces. There's a server that provides the functionality and the client. So the server is not necessarily the thing that defines the function, because it's just something that's providing the function. The server might also have a contract inside of it somewhere. But from the perspective of one contract, this is sort of the view of the world. So if our client provides a value to this function, then it'll first flow into the argument portion of the contract. If this fails, then we're going to raise an error message that blames the client for providing a bad value. If it doesn't fail, it will go into the server will perform some computation, and it will come, and some new value will be produced. Now again, we'll check the server side of the contract. If it fails, we'll raise an error message that blames the server. If it succeeds, it will come out, and if it's a higher order value, that the thing that comes out of the contract might have to also be wrapped with its own contract. So let's look at this in the case of that three layers of contract we stuck in the add function. Here it turns out we can blame the client, the first client. If that fails, we won't check any of the other contracts in the middle. If it succeeds, then all the others are going to succeed because they're all going to check the float predicate that we saw. Once it goes through add, though, if the result fails, we'll blame the server, or it will go through and pass through the others. So this is exactly the same set of blame labels that we can get if we just put one contract on there. So we like to be able to do this in general, but in the case of this one where we have a red contract followed by a blue contract, things don't quite work out. Here we would blame the client, the blue client, or we would blame the red server. And we can't remove just the blue part or just the red part and get something equivalent. We really want something in between the two. But right now, we don't have a good way to do that. So thankfully, there's been a lot of theoretical work on addressing this issue for various calculi. And these work well, and I think mostly solve the problem for, again, for small calculi. So as an inspiration for our work, we've built mostly on Michael Greenberg's work on space-efficient contracts. And we've introduced collapsible contracts. So the first thing is that right now we have these very opaque wrappers that we can't do anything with. If we want to get rid of them or collapse them or do something with them, we can't have this opaque representation. So instead, we will represent contracts with these explicit tree data structures where the trees basically match this sort of S expression representation of our contract, and I've shaded in the various parts that correspond to the other pictures. For the rest of the talk, float is always going to be a box, and the shadings are done to represent it. The diagonal hatched lines are always going to be things that would blame a client, and red would blame a server. So the other piece we want is that if we don't want to build up contracts, we need a way to combine them. So we want this merge function that's going to take two contracts and produce, hopefully, some smaller contract. And just as convention, we'll take the old contract that's already on a value first, and the new one that we're about to attach second. So every time that we attach a new contract, we'll call this merge function, combine the two, and put that value on our function instead of putting them both on. So here are the two contracts that from the example earlier. They're both the same contract, but they have different blames, so they're colored differently. So what happens when we merge these? We probably want to get a contract out that has roughly the same shape. But what goes in the leaves here? Let's try and get some intuition from what the opaque version looked like. Here, whenever the client passed a value in, it's checked against the shaded blue, then the shaded red. So in those positions, let's just do that. Let's check the shaded blue contract and then the shaded red version of float. In the result position, we'll do the opposite. We'll check the solid red, then the solid blue. So that seems like a reasonable result to get from merge. But that doesn't actually solve the problem that we're trying to address. We've just pushed it somewhere else. We've reduced the number of wrappers that we would put on a value, but we're still going to build up checks in the leaves. So since all of these boxes represent float, we don't actually need to check them all. Instead, we just want to keep the first one. So let's drop them and get something like this. So how can we write a merge function that does this? Well, I've done that for you. So if we combine two arrow contracts, we're just going to recursively call merge on the children. And just note that for client positions, we have to swap the order in order to preserve the right blame for error messages. So we can step through this with our actual merge definition. We'll push merge down into the leaves, swapping on the left, and then we'll do the same thing there. So now we just need to figure out what we need to do with these leaves. We really want this. We want, if we see the same contract twice, then we'll just drop the second one. We don't need it because we'll always check the first one first. If that succeeds, the second one must succeed. So that's what we'll do. And then we get exactly the result we want, which is something sort of in between the red contract and the blue contract, but isn't either. But let's take a look at this rule again, because this works if there's only one type of first order flat contract in our language. But that doesn't seem very likely. We might want to check if things are integers or strings or lots of other things. So to address this, we'll modify it so that if we try to combine the same contract twice, we'll get rid of the duplicate. But if we have two different contracts, because they're two different shapes, then we'll just keep them both. In the paper, we describe a way to do a little bit better than this, but this is roughly the idea. So for example, if we're merging float to float and positive to positive, then we do the same merge process, but because we have different contracts, we have to collect all of them here. So this ends up with fewer wrappers than it would before, but you still have the same number of checks. If we have a slightly different contract, like float to float and float to positive, then when we merge them, we can drop on the client side, but we have to keep them both in our results. So now let me talk a little bit about our evaluation. So we've implemented collapsible contracts in Racket. And for our evaluation, we are comparing two versions of Racket, a slightly modified version of Racket 6.12 with some contract-related fixes, and then that version of Racket extended with support for collapsible contracts. We have 20 different benchmark programs, which account for almost 7,000 different of these partially typed configurations. And now, what do we measure? So we have a bunch of these configurations which have some mix of typed and untyped code in them. So let's just figure out how long it takes all of them to run. But that's not a lot of information by itself. We really care about how these run compared to the untyped code, because we can use this as sort of a representative of how well or how much extra time is being spent checking contracts as opposed to actually running the program. So we'll just take this ratio, which we've been calling gradual typing overhead, and this is the main thing we've measured for both versions, but we've done this for both versions of Racket. And if we want to see how Racket with collapsible contracts compares against Racket 6.12, we'll take that ratio here. So ideally, if we were fixing up pathology, then this number should be very high, because there should be a lot of gradual typing overhead before we add collapsible contracts, and afterwards, we're hoping for a much smaller number. But ideally, we don't harm things too much in either direction, so if we're not getting a high number, we're expecting 1, give or take. So we've collected all of these in this histogram, and there's a few things worth pointing out. So thankfully, well, the sort of good news is that about 45% of our programs aren't really affected positively or negatively by the introduction of collapsible contracts. And this was probably the most significant amount of work to make sure that we don't affect things too bad. So we perform a lot of caching and other optimizations to make sure that our merge operation doesn't overly harm programs. So we do have some slowdowns, but our worst slowdown is by like 1.14x, which is definitely significant, but not too bad, and hopefully in the future we can fix that. On the other end, we do have some programs that have been sped up by almost 300 times, almost 30 times. So these are programs that exhibited a pathological issue beforehand and now don't exhibit the pathology. Somewhere in the middle, we have this bump around 1.2x speed up, which we didn't really expect this before our experiments or even while we were implementing this. So these are programs that we think exhibit some amount of this excessive contract wrapping, but also do other things that are, so they're not significantly sped up, but they do still exhibit some performance increase. So another way to look at these numbers is, here's a table of gradual typing overheads in Racket 612 and Racket with collapsible contracts. And ideally, all of these numbers are bigger for collapsible, which they are, but maybe not by quite as much as we would like generally. I think they're all about maybe 3% higher or less. So there's still a lot of overhead, even with collapsible contracts, but there's slightly less. So let's talk about the state of gradual typing. This paper was published at UPSA last year and claimed that gradual typing is only mostly dead. And so today, I think there's maybe a little bit more hope. We've shown that we can identify a pathology of gradual typing and address it without severely impacting the typical program. So today, I think maybe some gradual typing isn't mostly dead. Maybe some gradual typing is undead. Thank you.
Questions?
Hi, nice talk. You mentioned that when combining contracts, sometimes you can do better than just using both of them. That sounds a lot like subtyping and/or implication. Is my guess right, or can you say a little bit more about that?
That's pretty close. So Racket's contract system comes with a function called contract stronger that allows you to basically tell if one contract will fail at least as often as another, roughly. And so if we have a list of these contracts and an earlier one is stronger than a later one, we can just get rid of the later one. So yeah, it's basically exactly that.
Do you have an estimate of what's the upper bound of the maximum speed if you have perfect future work? Most optimistic.
The worst max slowdown that we have now is, I think, something around 1,000x slower than untyped. So as far as I know, that's like an upper bound for possible future work. I don't think we'll quite get there. I think maybe we can get things down to within maybe 10x slowdown, and then the rest will be a significant amount of work to make it faster than that.
Dan, in the original paper that we wrote, we analyzed 3 bottlenecks. One is application of primitive tests like float. Second one was allocation. You addressed those 2. But the third one, the biggest one that we could identify, was the checking of flat structures going across, like arrays, lists, hash tables. Can you see a way of doing collapsible contracts on, say, structures like that? Because that would eliminate a lot of the cost.
I think this idea.
It's really just a hint for future work.
Yeah, I think this is so. Besides functions, we also support vectors currently. So I think supporting further things like that is, yeah.
Hi, so quick question. So you phrased all your problems in terms of gradual typing, but really it seems your work is more generally about a problem with contract systems that are much more expressive than just serving as a substrate for implementing gradual typing. So is there anything that in your technique that's really restrictive to the gradual typing usage of the contract system, or is it more about contracts in general?
I think it mostly applies. It applies to contracts in general. We don't currently do anything that's specific to gradual typing.
All right, so it's really contract overhead and stuff. Yeah. Okay, thanks.
Any other questions? Okay, so
quick question. So the programs that you had the most speed up, were they the ones that had the most slowdown in the normal Racket, or you didn't do any analysis of kind of programs?
One of them, I think, one of them was previously a 1500x slowdown. That's the one that's been reduced by like 300, so it's down to maybe 50 or 30x. The other one, I don't remember offhand, but they were both they were large slowdowns previously. There's one more.
Okay, last question.
Do you do anything to try to distinguish between sort of overheads that are inherent in gradual typing versus overheads that are like incidental, more or less in the implementation of it?
I don't think so. Along the way, we found a lot of sort of stupid bugs that we fixed along the way that were sort of just implementation rather than necessary by gradual typing. There's definitely some slowdown that's inherent because you're adding these checks, but hopefully we fixed all of the stupid things and that we're getting down to just that.
Okay, let's thank the speaker.